afternoon, ladies and gentlemen. Welcome all delegates to the special lecture today for Inspiration in Science by the 2011 Nobel Laureate in Physics, Professor Brian Paul Schmidt. And my name is Natapon Chaptan. I'm your Master of Ceremony for today's event. And on behalf of the organizers, we are honored to be the host of this remarkable event. Today's lecture is part of the 5th ASEAN event series, Bridges, Dialogues Towards a Culture of Peace. And it's our privilege today to announce that Deputy Prime Minister, Professor Dr. Yuttawong, is joining us for today's lecture. And for now, I would like to begin the official opening of this event today. I'd like to, first of all, invite the Dean of the Faculty of Science, Professor Dr. Supahan Nongbua, to give the report on organization of this event. Ladies and gentlemen, please welcome Professor Supahan Nongbua.
Your Excellency, Deputy Prime Minister, Professor Yuttawong, on behalf of Faculty of Science, Kasetsart University, and all the participants gathered here today, may I express my gratitude to Your Excellency, Deputy Prime Minister, to have graciously consent to preside over the opening ceremony of this special lecture, which will be given by the 2011 Nobel Laureate for Physics, Professor Brian Schmidt. The goal of this event is to create and encourage the inspiration in science for our young generation, as we do believe that inspiration would spark innovation and a drive for discovery. Astronomy in particular is a popular subject in our Department of Physics for both academics and research. Astronomy was developed into a fundamental discipline of science in many countries, including Thailand. We see and realize the importance of the field in which human curiosity has been tested and led to one of the most important scientific revolutions in history of humanities. It is indeed a great honor that Professor Dr. Brian Schmidt, a 2011 Nobel Laureate for Physics, will gradually deliver a special lecture, Science, Humanities, Universal Bridge, right after the opening ceremony. In addition, this event is attended by over 600 participants from different high schools, universities, institutes from both government and industries in Thailand. We wish that the experience and knowledge from our speaker will inspire all of us for the great achievement and for the future development of science in Thailand. Excellency Deputy Prime Minister, on behalf of the organizer of the Inspiration in Science program, may I present Mr. Uwe Morawetz, Chairman of the International Peace Foundation, and Associate Professor Dr. Bodin Rasamite, Vice President for Sri Racha Campus, Kasetsart University, to deliver their addresses. And may I also have the honor to invite Your Excellency to officially open this special lecture. Thank you very much.
Thank you, Professor Han Nongbua. And now I'd like to invite Mr. Uwe Morawetz, the Chairman of the International Peace Foundation, to give a welcome address.
Excellencies, ladies and gentlemen, friends. Sawadee Kap and welcome to the 5th ASEAN event series, Bridges, Dialogues Towards a Culture of Peace. Bridges is facilitated by the International Peace Foundation, a non-political and non-religious foundation, under the patronage of 21 Nobel Peace Prize laureates based in Vienna. The events are hosted in cooperation with various local partners, including some of the major universities in Thailand, and I would like to thank Kasetsart University for hosting our event today. Having started in September, Bridges will now be continuously held in Thailand and Singapore until March, involving the participation of Nobel Laureates for Peace, Physics, Chemistry, Medicine, and Economics. The 5th ASEAN series of Bridges follows the series of 500 Bridges events, which the International Peace Foundation has already hosted in Thailand, the Philippines, Malaysia, Cambodia, and Vietnam since November 2003 as an independent contribution to the Decade for a Culture of Peace and Nonviolence initiated by the United Nations General Assembly. The pluralistic program of Bridges highlights the International Peace Foundation's intercultural and transdisciplinary approach towards peace. The foundation doesn't take sides, but acts as a mediator by creating an independent platform for dialogue where representatives of science, politics, culture, religion, the media, and youth can meet, share their viewpoints, listen to each other, and find mutual ways of understanding and cooperation. Therefore, the foundation itself is a bridge and a facilitator between different language groups in our divided societies, where politicians speak another language than scientists, and artists and business leaders another one than religious leaders. In a highly interdependent world, problems cannot be solved by either one of these language groups only, but by working together. After the success of its Bridges programs in Thailand, the Philippines, Malaysia, Cambodia, and Vietnam, the International Peace Foundation has been invited by other ASEAN countries to build further bridges towards peace and international understanding by expanding its program in Southeast Asia to stimulate the intellectual, intercultural, and scientific exchange in the region. The 5th ASEAN Bridges series therefore continuously takes place in Thailand and Singapore from September 2014 to March 2015, comprising events with Nobel laureates from all fields. The Nobel laureates visit the region not all at once, but separately conduct public lectures, seminars, workshops, and dialogues hosted by local institutions during a continued period of 6 months. The topics of the ongoing events deal with the overall theme of building a culture of peace and development in a globalized world, and with a wide range of issues in the fields of politics, economy, science, culture, and the media. They especially highlight the challenges of both globalization and regionalism, and its impact on development and international cooperation. The aim of Bridges is to facilitate and strengthen dialogue and communication between societies in Southeast Asia with their multiple cultures and faiths, as well as with peoples in other parts of the world, to promote understanding and trust. The events aim at building bridges with local universities and other institutions in Southeast Asia to establish long-term relationships with Nobel laureates in all fields, which may result in common research programs and other forms of collaboration. By enhancing science, technology, and education as a basis for peace and development, the events may lead to a better cooperation for the advancement of freedom, peace, and security in the region with the active involvement of the young generation, ASEAN's key to the future. This is why Bridges is not designed as a one-time event, but as a series and a process of synergies to make the events a sustainable success for Thailand, Singapore, and for the region as a whole. I am grateful to Kasetsart University, as well as to our other partners and sponsors, who have enabled us to make the idea of bridges a reality. I would like to say thank you to everyone present today for taking part in this program. May it help us to facilitate a new culture of peace through dialogue, transcending the definition as merely the absence of war or armed conflict into a new understanding what the basis for peace is: education. In this spirit, we welcome today the 2011 Nobel Laureate for Physics, Professor Schmidt, who has agreed to come to Thailand to support the events. We look forward to his keynote speech and to his important contribution to build bridges. Thank you very much. ขอบคุณมากครับ
Thank you, Mr. Morawetz. And may I ask you to remain on stage for a few moments? Please, can you please? Yes. Thank you very much. On behalf of Kasetsart University, we would like to thank the IPF and Mr. Morawetz for supporting us at this event. And may I invite the Vice President of Kasetsart University, Siracha Campus, Associate Professor Dr. Vindicated, to present the token of appreciation from Kasetsart University. Ladies and gentlemen, please join me to thank IPF for this event. And one more token of appreciation. Thank you very much. And now I'd like to invite the Vice President of Kasetsart University, Siracha Campus, to continue giving the speech for the welcome address for today's special lecture. Ladies and gentlemen, please welcome Associate Professor Dr. Vindicated.
Your Excellency, Deputy Prime Minister, Nobel Laureate, and ladies and gentlemen, all participants, all professors and students, welcome to Kasetsart University. It has been a great pleasure and another good day for us to come here and listen to one of the greatest minds in the century. I think many of you who probably have been here for the first time, especially the speaker, I have been sitting with him for about half an hour and try to ask him to probably come and stay with Kasetsart University more often. So I hope to see you more often from the years to come. And on behalf of Kasetsart University, just to make it short, we really appreciate the bridges, the speaker, and all the participants to come here today and to participate in such a great event. Of course, education is the beginning of peace. So today marks the beginning of another good day, another peace for the years to come. And thank you very much for coming. Welcome to Kasetsart University, and hope you learn something today, all the students who come here. Okay, learn something, get something, and you will be able to use it in your exam. Thank you very much. Welcome to Kasetsart University.
Thank you for Professor. And ladies and gentlemen, it's now the time for official opening of this today's special lecture. I would like to invite His Excellency, the Deputy Prime Minister, Professor Dr. Yonghyut Yuttawong, to address the opening speech. Please welcome Professor Yuttawong.
Professor Dr. Brian Schmidt, the President-elect of Kasetsart University, Dr. Vindicated, congratulations, by the way, for being selected the next president of this very important university. Dr. Morawetz, distinguished guests, ladies and gentlemen, I have a note here prepared by Dr. Supha, and I have read this, very nice, but I think I will just shorten the time so that you can hear what you want to hear more quickly. Professor Schmidt is going to talk about science as humanity's universal bridge, which is really suits well with the theme of Bridges, International Peace Foundation. Many of you might wonder or might want him to talk about the expanding universe. That's what he got the Nobel Prize for. But maybe you can talk with him later. I'm sure that he will have lots of time to talk about expanding universe. But today, I think that his work actually goes well and is even broader in terms of science as humanity's universal bridge. So note that the word universe is there. Because I think that science is really a universal language, and you can talk to people on the basis of their innermost desire. That is the desire to understand nature and the desire to really be able to use knowledge for human benefits. So I think that is what I anticipate. Maybe he will talk about something else more, but I think that that is really a crucial theme. Whatever we do, whether we work on expanding universe or tiny molecules, it's really our urge to understand what is there, how to explain it, why and how. And I think this should really inspire us all here. And we are also, it's also nice for scientists to be able to contribute not only to the understanding of the universe, but also to the benefits, like all the good things that surround us really come from science and technology, a lot of them. And for this century, I think we will also need to make our understanding go, a long way towards sustainability. Because in the past, we've really used science with such force that sometimes we tend to neglect the natural surroundings, the environment. So this century, the keyword is sustainability. And I'm sure that science will also be able to deliver sustainability to our efforts. So without further ado, I think I would like to open the special lecture which commemorates the 72nd anniversary, and I'd like to congratulate the organizing committee for the success of this event, and gratitude to the International Peace Foundation for this excellent collaboration. So thank you very much.
Thank you, Mr. Deputy Prime Minister. And may I ask you to remain on stage for a few moments, and I would like to invite Professor Vindicated one more time to present the token of appreciation from Kasetsart University. Thank you, Mr. Deputy Prime Minister, for joining us today for the official opening of this event. And ladies and gentlemen, now it's time for the lecture, but before we begin the lecture, I'd like to give you a short CV of Professor Brian Paul Schmidt. Professor Schmidt received his bachelor degree, Bachelor of Science in both physics and astronomy from the University of Arizona in 1989, and he received his Master of Art and his PhD in astronomy as well from Harvard University in 1993, and currently he is holding a position as a distinguished professor at the Australian National University, and he's also an Australian Research Council Laureate Fellow. I have a long list of his awards here in my hand, but the most important one is in 2011. It's the Nobel Laureate in Physics for the discovery of the evidence that the expansion of the universe is accelerating. Now it's time for the special lecture to begin. Ladies and gentlemen, please join me to welcome 2011 Nobel Laureate in Physics, Professor Brian Paul Schmidt.
Ladies and gentlemen, it's a great privilege to be here. Deputy Prime Minister, members of the university, Uwe Morawetz, students from local high schools, and members of the university, and members of the public. What I'm going to be talking about is something that really strikes at the heart of what I am passionate about, which is how science interacts with all of humanity. I think we inherently know that science has brought much of what we have today that makes life prosperous. But I think it's worthwhile giving it a slightly deeper thought about how science really does contribute to the society we live in today. I want to first think in the longest possible terms about humanity's relationship with science. I show here a set of stars known as the Pleiades, or the Seven Sisters, or any countless numbers of names. But it's a set of stars, and if we can see them, it turns out, from essentially every place on planet Earth where humans have ever lived. And every society, planet Earth, has recorded these stars. And what is quite remarkable is their story of the stars is very similar. So the Pleiades is a group of stars about 200 million years old. They have been around since the time of the dinosaurs. But when we go through and see what people describe them as, the Greeks, the Pleiades, or the Seven Sisters, the Australian Aboriginals, isolated from the rest of the human species for tens of thousands of years, also calls them the Seven Sisters. Ancient Indian, they were known as the Seven Virgins. And here in Thailand, they're known as the Seven Chicks. You can see a common theme. This is a story that goes back to prehistory. It is a story we all share, and while it is difficult to prove, it is quite likely that the notion of this being 7 young women goes back to the earliest days of humans as a species. It is probably the oldest thing we can identify that we all share around the world. Now, it's not universal in all cultures to be 7 young women. For example, if you go to Japan, it's known as Subaru. And I am not, although I drive a Subaru, I am not telling you to go out and buy one. But I want you to look at that emblem. That emblem only has 6 stars. And indeed, for any person with normal vision, there are 6 stars there, not 7. That is, when you look at the Pleiades with your eyes, rather than looking like this, they look more like that. Okay, and that's because your eye is not the Hubble Space Telescope. It doesn't have the sensitivity or the resolution. So why 7 stars compared to 6? I don't know. But the fact that there are 7 stars in all of those stories, despite only being able to see 6, helps trace that lineage back tens of thousands of years into our past as humans. And quite remarkably, the lineage goes back and recorded history to the earliest times of recorded history. This is a painting from a cave in France. It is 17,300 years old. What we see there, we see the bull, also known as the constellation Taurus. And we see the Pleiades, right where they should be, above the bull's shoulder. The 6 stars. Note, what is the constellation name for this area? It is still Taurus the bull. 17,300 years ago, it was Taurus the bull. It wasn't called Taurus, that's the Greek name, but it was the bull. So the stars are in our collective history from the beginnings of humanity. And I find that profound. It is the thing we have together, longer than anything. Every human has seen the same set of stars. And astronomy and the stars are what got science going in our own world and has led us to the point civilization has reached today. Here we see Ptolemy, the Greek. And Ptolemy had an idea. He had an idea of trying to predict how the planets moved across the sky. And to solve this, he had to live within the axioms, or the rules of the day. The rules of the day were very clear. The Earth is the center of the universe. And objects must travel in circles. So to do that, by constructing complex patterns that look like a spirograph, a toy I played with when I was young, he could very accurately predict the motions of the planets across the sky. So successful was he that his tables were used through the medieval ages to predict where the planets were and important things, for example, of when Easter would occur in the future. That universe seemed correct to the people of the time. It worked so well. Why would the Earth not be at the center? Why would the planets not travel in circles, within circles, within circles, which we call epicycles? Well, it took until the 15th century for people to go past this axiom. And that came from Nicholas Copernicus. He realized that if he got rid of one of the axioms, which is that the Earth is the center, but he still needed to keep the planets traveling in circles. That remained an axiom for Copernicus. He could also predict the motions of the planets in a much, much more simple diagram. You can see that Copernicus's diagram much more simple than Ptolemy's. But it turns out he didn't have the time to refine it like Ptolemy, and he could actually not predict the position of the planets as well as Ptolemy. So why was Copernicus taken seriously at all? Well, it was because it seemed at the heart of it a good idea. Within science, we have a rule. The simplest idea that explains the world is the one that we believe in. We call that Occam's razor. The simplest idea that explains the observations we make of it. And it really took until Galileo invented a piece of technology. And that technology was the telescope. He did not invent the telescope. Rather, he took the telescope and improved it. The telescope was made so it could be used to focus on the distant stars. And with it, he could look at things. He could look at a planet. And the planet, when you look at the planet, Jupiter, for example, instead of looking like a star, it became an orb. An orb orbited by 4 other orbs, moons. It was very clear that Jupiter was the center of its own little universe. That is, that idea, that axiom of Greece, that the Earth must be at the center, was wrong. It was demonstrably false. And he could see it also when you look at, for example, Venus. Venus showed phases. When Venus was going around the sun and on the Earth's side of the sun, it was big. And it showed a crescent phase like the moon does when it's only partially illuminated by the sun, our part that we see. When it was a long ways away and fully illuminated by the sun, it was small, just like Copernicus's method suggested. So it was with his own eyes that Galileo showed that Copernicus's view of the universe was the correct one. And Galileo was a brave man. He decided it was one thing to write about it in the Sidereus Nuncius, but it was another thing for others to see with their own eyes. And so he made telescopes and gave them away to people of influence, including, for example, the Pope. This turned out maybe not to be his best choice in his life, but it was the means by which he convinced people, and really the world, that Copernicus was correct. So, then came along Newton. Newton was fascinated by the motions of the planets. And to understand them, he invented the idea of gravity. But gravity was new, because not only was it an idea, it used mathematics. It used mathematics to be able to predict from a very simple law of gravity how the objects of the universe would move around. And there was born, between Galileo and Newton, the modern philosophy of science, of prediction, of testing, of revision when necessary, of retesting. The cycle goes on. It was used, for example, in the discovery of planets beyond the ones that we knew from ancient times. In 1781, using a modern, very large telescope, William Herschel went out and accidentally discovered Uranus, a faint object, too faint to be seen with your eye. And when they plotted Uranus's motion around the sun, it suddenly violated Newton's laws of gravity. It did not go where it was supposed to. there was a slight problem. Did that mean that Newton's laws of gravity were wrong? Maybe. But someone else had another idea. A Frenchman, a mathematician, who said, all what we need to do is add another planet, Neptune. And if it's at precisely this position, it will make Uranus go around the sun as we see, with Newton's laws intact. And in a rare form of Franco-German cooperation, the Germans went through and observed the prediction of the new planet and found it almost immediately. That is the power of science, is prediction and testing. The prediction was made. Was Neptune real? Not until we observed it. And then we knew that, once again, Newton was right, and that there was something new about the universe we knew. We had a new planet. Of course, some other people came along and thought about the universe in other ways. I want you to look. This is a picture of a bowling ball and a feather. And Brian Cox has gone through extraordinary efforts to look at this thing. And we're dropping. You probably don't need the sound, but okay. So the balls are falling. The feathers are falling. They're falling at exactly the same rate. Just as we all know and are taught it should. But when Einstein looked at that, he thought about it. And he actually didn't look at a bowling ball and a feather. He looked about someone who was painting a house. And he imagined if they fell, they would not feel gravity. And that the motion of falling would be exactly counteracted by gravity, perfectly. And he thought, I think that must always be true. Very simple thought. And that thought, which is that effectively, if I put you in a box, you cannot tell by any scientific test if you are in a box on Earth being accelerated 9.8 meters per second squared by gravity, or if you're in a rocket ship accelerating at 9.8 meters per second by gravity. They are equivalent. Now, that seems like a subtle thought, but it is a thought that took Einstein 8.5 years to figure out. And while many of us know of E equals mc squared, the physics world would say this is Einstein's crowning achievement, realizing that acceleration due to gravity and acceleration due to motion are interchangeable. And it predicted things. It predicted that Newton's law of gravity shouldn't be exactly right in all cases. It predicted that space should be curved. And that if you go through and look at an eclipse, for example, the stars around the eclipse, because the sun curves space, should be in a different place when the sun is not there. This is something that Arthur Eddington went out and tested, and in 1919, 1920 demonstrated it was true, and this is the moment that Einstein became a household name and world famous, because he had a thought, a pure thought alone, a thought which demonstrated an idea which could be tested. It is really almost unique in human time. I'm going to have a brief interlude as we fix my computer to give us the entire screen. But I'm going to keep talking to keep us entertained. So, it was a unique time in scientific history. Most science is we have a problem. We want to solve it. we come up with an idea to solve it, we test that problem to see if the solution works. Einstein had no problem to solve. He had simply a thought, and he said, it seems to me it would make sense that acceleration due to gravity and acceleration due to motion should always be the same. Copernicus really had the same revelation. There was no reason to say Ptolemy was wrong. It was a matter of aesthetics. But those two times are almost the only times in history that that has occurred. All right, I feel a whole person now, as I have my entire talk behind. So, the telescopes went out and vindicated Einstein's theory of gravity through the observations of eclipse and made him famous. So, throughout history, you can see through the stars the development of how science works. And I want you to ask yourself, what is reality? What is real? And I claim that reality is a set of ideas that each of us have that predict what we see. And if we cannot predict what we see, then that part of the universe, we are unsure what is real and what is not. When we think we understand everything, then we think we have reality under control. For 200 years, gravity was as Newton described. Then suddenly, reality changed. Space is curved. Our notion of gravity was different. But isn't? When I teach physics to high school students or to students in my classes, I always teach it, at least at first, as Newton's laws of gravity. When I think of dropping a ball here, I don't think of it in terms of general relativity. I think of it in terms of Newton's laws. So what's reality? Newton's laws or general relativity? Well, it turns out general relativity is better, but it's not the way I actually think about it, and almost no physicist thinks about gravity, unless you're around a black hole, as Einstein was. And so reality can change, and our perception can change. So why do we do science? Well, the minister, and since we have a deputy prime minister here, who actually is a scientist, so he's rather unusual compared to the ones that I have in my own country. I'm asked this question all the time. Why do we do science? And I always give the answer, because it's interesting. That is why we do science. And he scratches his head, says, all right, let me rephrase the question. Why do I pay for science? That's a different question. Well, the reason governments pay for science, it's not really because it's interesting. They pay because it is valued. Science, it turns out, is the way we predict things. And when you can predict things, you can build things, you can make new things, you can create technology that helps solve problems. And that is the foundations of why science is valuable. It's prediction. Some people see science as almost a religion. To me, it's a way of, I think, best dealing with information in our universe. It's a way that we can go through and take, for example, the knowledge that one of my colleagues in Australia gathered looking for evaporating black holes, predicted by Stephen Hawking, and failing to find them. Was his career a failure? No, because the knowledge he used to look for those evaporating black holes, he later used to develop Wi-Fi, a Australia's most valuable invention. So when my minister says valuable, I remind him about Wi-Fi and countless other inventions that come out of basic research. Why? Because it turns out if you don't do basic research, you only invent what you already know. And the whole point of research is that we don't know what we're doing. That's Albert Einstein's view, is if we knew what we were doing, it wouldn't have been called research. So you don't spend all of your efforts doing research, but you spend part of it. And then you spend part of that money beyond developing your ideas and making progress. But you need to do both. Governments love to only do one. Just make the product. Don't do the ideas. That works for about a year or two, and then you run out of ideas. So, there are no shortcuts when it comes to science. And I will argue that science has transformed humanity in our life. And the best way I can think about that, most easiest, is looking at the human lifespan over time. In the earliest epochs, the average age from fossil records of humans 40,000 years ago, 32 years. If we look at the Greeks, 28 years. They were too busy killing each other with Spartanese. The Romans, 30 years. They had managed to get rid of wars by winning all of them. Medieval Britain, it's only 500 years ago. 30 years. The world in 1910. 31 years. And then what happened? The scientific revolution has happened. The thing that allows us to have better and better lives, despite what we see around us as all these problems. The reality is that the average person in the world from 1910 to 2010's lifespan has gone from 31 years to 67 years. The longest country above that, Japan, is 80 years. So it is quite narrowly defined. There are a few places which the lifespan is still very short. Swaziland is still almost down to 31 years. They have almost no impact of science in their culture. But there is a price. There are lots of us. We're living longer, which means that we can multiply, and we have. If we look at the number of people around the world over time, you can see that until about 5,000 years ago, when we got the first vestiges of technology, we were steady. And since then, it's been a rise until literally 1900, where the scientific revolution has allowed us to exponentially increase in numbers. Now, you don't have to be a scientist to realize you cannot exponentially increase forever. Here is the world energy consumption, shown in a more recent time scale, and this is a consequence of the fact that there are more and more of us wanting more and more. And you can see that the amount of power that we're using is rising sharply even today. And that has consequences when, for example, we look at the number of trees on planet Earth. Trees have the nice effect of consuming carbon dioxide and turning it into oxygen. Indeed, in the future, when we're going to be looking for civilizations on distant planets, the easiest and best way for us to find that is to look for oxygen in the atmospheres of distant planets, which we can do when they go in front of their stars, and their light of the star shines through the atmosphere. But here on planet Earth, we know if we were to do that experiment, if we would compare how much, for example, carbon dioxide there is in the atmosphere, it has risen sharply over the last 50 years. And the number of trees has dropped sharply. And that's simply because we are right now not sustainably using the Earth's resources. The amount of energy that each of us use times the number of people is more than what the Earth can sustainably withstand. And the solution to this is going to be technology backed by science. So technology, note, is also what has caused our problem. That exponential increase in the number of people and our energy consumption is also based around the science. So technology can be a double-edged sword. It does not solve things in and of itself. Life can be made better by technology, but it can always make its own problems. And so for humanity's future, it is imperative that we focus on using science and technology to solve the world's long-term problems, not just its short-term ones. Now that is something that humanity has actually really never, ever done. It has never tried to solve problems 50 years in the making. It has always concentrated on the 3 to 5 year time scale or less. And science can help. For example, with abundant energy, the Earth can support, I think quite easily, the 8 billion people on it if we have the right technology. And abundant energy seems to be a problem now, although with the price of oil dropping dramatically, it seems less of a problem immediately. But it will become a problem again. But science can help. Why? Because it turns out that the world uses right now about 16 terawatts of electricity continuously. And if you look at how much coal there is, we have hundreds upon hundreds of years of energy, but the coal causes problems. But all of this is dwarfed by the amount of solar energy, 10,000 times more than what we really need, or 1,000 times more than what we really need. But we also have, in the form of wind and other forms of renewable electricity, more than enough to even increase our energy supply by factors of 2 or 3. But it does require technology, and it does require sharing, as I'll show you. Science can only be the bridge. Science can provide the means to prosperity, but only if humanity is willing to share the world, the technology, and the affluence that each person on Earth wants for their own. We have to realize that until all 7.5 billion people on Earth feel that they more or less have the same quality of life of everyone else, the people who have less are going to want more. But once people have a lot, enough, not less than everyone else, they're usually pretty happy. It's a fundamental part of the way humanity has worked. While science is our best means to find the solutions we need to make everyone affluent, we should also keep in mind science is not guaranteed to find a solution. There may be, we are capable of making problems too hard for science to fix. And it may well be that science will be too slow to fix the problems. So we need to give ourselves the best shot, give us the longest time to try to fix our problems. I should say that science is already a bridge. Here is a newspaper headline from earlier this week. We are working together with many, many nations in space while we quarrel with Russia about issues on Earth. We have a problem in space, and all the American astronauts immediately are able to take refuge in the space station. We work together there all the time. There was no question about it, it just happened. This would not happen on planet Earth. So we're capable of doing it, but it requires a different way of thinking. And science is a way that the world communicates. It's the same language around the world. It's of knowledge. It's of sharing. It's of moving forward together. And the amazing thing about science, and this is why humanity has been able to get to where it's at, is that every good thought by any person on Earth for the last 50 years has been able to be shared with every other person on the planet. So if someone comes up with a brilliant idea here in Thailand, I will be using it within a year in Australia, and vice versa. That is what science gives us. It gives us the ability to work collectively together to solve the world's problems. And we do this. For example, if I look in Australia, more than 20% of all the people going to our universities are from places other than Australia. There are roughly 3,000 Thais studying in Australia as undergraduates and graduate students. And you can look at the fraction in Australia, for example, of our scientific publications. 45% of all the science we do involves people from other countries. And obviously, the bigger the country and the more science it does, the more we work with it. Well, let's look at who we work with based on the size of the country. It's quite remarkable. New Zealand makes sense. We work a lot with New Zealand. Why? Because it's nearby and culturally very similar. We actually have a lot of governmental things that allow, for example, me to take a New Zealand student for no cost whatsoever. But then countries like Singapore, well, it's nearby. It also makes sense. South Africa, so we work preferentially with South Africa compared to the United States or Europe. The United Kingdom, again, we have long-term links. Iran. Now, anyone who's been to Australia knows there's not a lot of love, at least at the governmental level, between Iran and Australia. Yet we preferentially, given the size of our scientific cohort, preferentially work with Iran. That is the beauty of science. It allows you to build bridges over the political obstacles that separate us all. So humanity has some big challenges ahead of it. You might ask, what are they? Is it health? Is it life expectancy? I would argue no. The average age of the world is 67. The question is the average quality of life of those 67 years equal around the world? The answer is no. People have much different qualities of lives around the world. So I don't think it's longevity, but I think it's quality of life that we're looking for. Quality of life is due to things like food, access to food, water, energy, accommodation. In order to sustainably have high levels of that, you need to have good education. People need to have positive employment prospects. You need to have stability of government, and you need to feel safe. Those are the things that make up quality lives. And how are we going to achieve that? Well, it turns out that one thing is we cannot keep exponentially growing. But there's something on our side here. Here we plot the fertility, the number of children the average female of a country has, based on the average income. And it turns out if you're poor, you have lots of children. And if you get rich, you have fewer. The dotted line is the replacement rate, where the world quits growing. Quite remarkably, the world is almost already, given how affluent we are, at the point where we're going to quit growing. Not there yet. But the key to keep the world sustainable and having 8 billion or 9 billion people in it rather than 30 billion, because I don't think anything I can do will save the Earth if we have 30 billion people on it over the next 100 years. is to make people rich. And if you look at how many people will be in the world and the projections, if we are able to continue to make more and more people prosperous, we will flatten the number of people out on the world out at about 8.5 billion people. So that has to be a goal. The thing that I think that needs to happen for that to occur is we need to achieve an equal level of prosperity across the entire world. That has to be the aim. That will stabilize the population of the Earth. It will lower the drivers of conflict, which ultimately will be the things that destroy us if we do not manage sustainable Earth. And it will allow the entire world to focus on living sustainably through advances in science. So it's the tool, but it requires more. So, we should not underestimate the current challenges. The challenges of climate change already upon us by not focusing over the last 100 years on the future are not small. The changing weather patterns are going to affect agriculture. We need lots of research in agriculture. And this university specializes in that. And that is an area which Australia specializes in. It is going to be imperative that we have sustainable fuel supplies as the Earth's climate changes over the coming decades. There will be different water resources available. For example, here in Asia, especially some of the neighbors to Thailand, the glacial runoff from the Himalayas is going to dramatically change. And this is going to lead to changes in the way agriculture can proceed. This is also going to happen in the Pacific Northwest of North America and in parts of Europe. And finally, rising sea levels are upon us. And when I go down and around here in Thailand and I see all these houses on piers, you know, what looks to me as being a very small distance above the water, you realize that things are going to have to change. All these factors can be managed with technology. It's not cheap, but they also have the potential to create conflicts over the resources. So we can work together and we can manage these with technology. But if we don't, we will fight over the consequences. That is the big thing that we, as humans, need to think about over the next 50 years. So the future prospects for humanity. Well, I know we can manage these problems. Will we is another question. So I want you to think about this in maybe a more abstract way. Humans have been on Earth for 100,000 of Earth's 4.54 billion years. To put that into an analogy we can think of, if we are finishing the first day, a day, the Earth's whole life is 1 day, 24 hours, then humans came onto the scene at 2 seconds to midnight. That is, we are a tiny speck of the life of Earth. So we haven't been here very long. And think how much we've done to the Earth. We completely dominate what the Earth is doing. So what can we expect for the future? Well, we need to deal with climate change that we've done ourselves. But I told you there are things that go beyond just human intervention. We can expect supervolcanic eruptions. This part of the world gives us our share. Where I grew up in Montana also gives us share, Yellowstone National Park. They happen every 5,000 years. They conveniently cool the world down. It turns out in the old days that was a bad thing. But given the current state of the Earth, it may not be the worst thing. But they will have dramatic effects on Earth's agriculture when they do occur. So we need to be able to be prepared for those and manage it. When might this happen? It could happen next year. It could happen 50,000 years from now. Don't know. You can't predict, you can prepare. The Earth itself has periods of warmth and cold Now, we have, and those sort of have 50,000 year cycles. We can manage those, as we are already. We can heat the Earth up if we want. We can also cool it down. We don't really know what we're doing, and I wouldn't recommend doing this geoengineering, as it's known. But we have the potential, at least, to understand it for the future as a way to combat something that we don't expect. Longer term, comet and asteroid impacts. Those happen every 50 million years or so, where a huge impact comes that the size that if it happens, it would cause extinction of the entire human species. But the amazing thing is we have the technology already in place to stop this from happening. We need to prepare, and this is why people around the world are using astronomy to chart bits of rock and ice in space to make sure none of them are going to bump into us. Because it's not likely to happen in the next 100 years. You'd feel pretty foolish if it did, and you weren't prepared. And finally, the thing that I don't know how to get around is the sun. The sun, which gives us all that nuclear energy, its nuclear reactor is heating up. And it will boil off the Earth's oceans 500 million years from now. Then it'll be time to move to Mars. But it turns out that'll gain us a bit more time. But eventually, the sun will pop up, destroy the Earth, Mars, and it will be time to move to a new solar system around a new star. So we have a lot of time to figure out how to do that. And if you've watched the movie Interstellar, I don't think it's going to be that easy. But with time, I cannot tell you what humans are capable of. I simply don't know. I know that science will be the thing that will allow us to get around each of these obstacles and to get around the more short-term obstacles I've already described to you. Eventually, one can ask, how is this going to work? I would say, wearing my scientific hat, we are up against it to let it last forever. This is an image of our galaxy, the Milky Way. It has 100 billion stars in it. We estimate there are 20 billion habitable planets around that galaxy. And that galaxy is roughly 100,000 light years across. If we look beyond that, we see a universe which is full of galaxies. This is one tiny speck of the sky, has 20,000 galaxies in it. We are truly a drop in the ocean. But let's think about what we can do if we figure out how to travel to the nearest stars and increase our longevity beyond just the life of the sun. Well, the nearest star, Alpha Centauri, right there, if you ever come to Australia, one of the brightest stars in the sky, points to the Southern Cross. That's 4.3 light years in distance. So it turns out that with the fastest spaceship we've ever made, we can get there in about 26,000 years. So we have to figure out how to live 26,000 years on a spaceship. Well, let's imagine we do that, and we're not able to go any faster. Now, presumably, we'll figure out how to go faster over time. Well, let's just say we're going to go at our current speed. 26,000 years to the nearest star. What are we going to do? We're going to get there. We're going to hope it's going to be one of the ones that has a habitable planet. 20% of all stars have habitable planets. Probably not going to choose the star. It's a binary star. So we may choose one that's nearby that does have a habitable planet, because we can start identifying those habitable planets now already. And Alpha Centauri does not obviously have one. Nonetheless, let's then think about going around the galaxy. Once we get to a habitable planet, what are we going to do? We're going to grow up, we're going to use it, and then we're going to need to move on. And we'll move to the next one, and the next one, and the next one. It turns out it only takes us at that speed 600 million years to go across the entire galaxy. So imagine some civilization on those 20 billion stars has figured out how to travel from star to star. Well, they've had 13.8 billion years, so unless it's happened just recently, they will have gotten to us. And yet, I personally have not seen an unidentified flying object. I have seen no evidence for aliens. And this is known as Fermi's paradox, which is, if in the past 13.8 billion years, any civilization has mastered interstellar travel, they would have had time to spread across the entire galaxy. Yet we see no such civilization here on Earth, meaning it would appear no civilization has managed. So the bar is high. Will humanity be able to be the first? I don't know. The odds are against us, but the only way it's going to happen is through science. And on that moment, on that note, I will finish. Thank you very much.
Thank you, Professor Schmidt, for a fruitful lecture so that we could learn and be inspired to use science as a bridge for the betterment of humanity. And now the floor is open for questions and comments from the audience.
Don't be shy.
I
Excellent.
think now we have many scientists and many students in this room. I think I want to ask you about what is your inspiration for your work and how to finish your inspiration.
All right. So I like to understand how things work. I have been like that since I was a little kid. Scientists around the world are those who like to figure out how things work. It turns out when I go anywhere in the world and I meet 10-year-olds, they're always curious. They're always asking, how? How does this work? How does this work? How does this work? We are born curious. We are all born as scientists. Somehow we manage to squeeze that out of many people, but not all. The ones who have that innate curiosity are the ones destined to be scientists of the future. So, for me, it's part of who I am, wanting to understand, to solve the puzzles. And in terms, the second part of the question,
How you're finishing your inspiration for your work?
how do I?
Finishing. How you manage yourself?
So, you know, you don't, in my case, you're always looking for the next problem to solve. There's questions. There are more questions than there are answers, always. So science never finishes. It just goes. And you take one step, you make another step. My discovery, my team and myself, of the accelerated universe, that goes way back to Galileo, right? If Galileo hadn't realized about the telescope and the notion of how objects were moving around the sun, that inspired Newton, which inspired Herschel, which inspired Einstein, etc., I would have never been here to make my discovery. We all depend on the questions and answers the previous generations have brought to it. And that will never change. And discoveries in the future will use my discovery, but they will also use countless other discoveries made by scientists around the world, which did not win a Nobel Prize. And you never know in advance which of the discoveries of the past are going to be important for the future.
Thank you very much.
Have a question in the front for microphone ด้านหน้า
I just wanted to ask, how did you make the leap from high school to PhD? I mean, what was the path?
So I grew up in a very remote part of the United States, Alaska. Much more remote than Bangkok is. Okay? I was a normal student. I wasn't the savant, the person who was always going to do great things. My high school teachers were surprised that I won a Nobel Prize. I was a good student. It wasn't that they thought I was a bad student. But I was just another good student. You know, they'd had many other students. They said, well, we had had students better than you. And I said, yeah, that's true. So science is done by many, many people. There are many, many hundreds of thousands of people around the world doing great science. And by doing that, humanity is covering all of these areas of unknown, things we don't know. Occasionally, someone like me makes a discovery. Why me? I was lucky. I was born at the right time. I did good work. But there are hundreds of thousands of others who are also doing good work. And people say, when do you know you're going to, when do you think, when did you know you're going to win a Nobel Prize? And the answer is 8:39 p.m. on October 4th, 2011, when they called me up. Okay? Did I think I was going to win a Nobel Prize when I was in high school? Are you crazy? No. I didn't even dream. I mean, it wasn't even a dream. It was just, I just wasn't going to be me. Now, I realize that Nobel Prizes are won by smart, but relatively normal people who get lucky, in most cases, of being at the right place at the right time of doing great things. The Nobel Prize is the celebration that humanity has about science. We award individuals, but it really is a celebration of science. You note that my team, 20 people, made the discovery. It wasn't just me. And I get to be the poster child who talks about it. But the reality is, it was a joint discovery. Many people working very hard for many years based on thousands of people's work. Okay, I'll explain the rest. So my own personal story of getting from point A to point B is I finished high school. I knew I wanted to study science. I always thought I was going to do meteorology. I went and worked at the Anchorage forecasting station of the U.S. Weather Service and realized that forecasting isn't really science. It's meteorology, but it's not the type of science of discovery I want to do. So I didn't know what to do. So I said, I will go on and do astronomy. Why? Because I didn't know what else to do. I never thought I would get a job as an astronomer. I just didn't think I was that smart. My teachers agreed. And they were probably right. But the reality is I did better at university than they expected me, because I've always been able to keep on learning. And so I went off to the University of Arizona, which is a large state school, not dissimilar to this university as it fits in Thailand. If anything, this is a better university in Thailand than the University of Arizona is in the US landscape. And there I did very well. I worked hard, and I did finish at the top of my university. That allowed me to go to graduate school. I had no one from my university within 10 years had gotten into a very good graduate school, but I was the first. So I was able to choose, and I ended up choosing Harvard. And there I got my PhD. And then once you get a PhD from Harvard, it doesn't mean that the world is paved in gold. You then have to go out and get a job. And in my case, my wife, who was also doing her PhD at Harvard in economics, and I had to apply for jobs around the world. And not only did I have to get a job, she had to get a job, and we had to get them in the same spot. And it turned out Canberra, Australia is where we got our jobs. And turned out to be very fortunate. We both got very good jobs there. And that enabled me to give me the environment to sit down and do my work. And that eventually led to the discovery of accelerated work.
more questions. There is a question in the back. Microphone.
Yep, microphone, yep.
Hello. Thanks a lot, sir. It was a really nice lecture. If you show us in the form of like percentage, how much is the luck and how much is your work? What do you think?
Well, when you make a Nobel Prize discovery, you actually have to do the work that makes the discovery. But the point being is there were many, many people who had, if I never existed, someone else by now, I think, would have discovered the accelerating universe. They would have done it by doing the same types of thing that I did. So my uniqueness is not important. It's doing. Humanity, we always, I've got to meet pretty much any famous person in the world. And I'm always struck because, like all humans, I look up and I say, this person is famous, is beyond me. But they're not. They're people just like you, who have been chosen by talent, but also by circumstance, to do what they do. And so, I'm not unique. I'm a person who's been given opportunities. I've had luck. I did good work. Someone else would have done it eventually.
So it's a kind of combination, you can say.
Well, I wouldn't call it communism. I would say it's more like fatalism. Right? Humanity works so well, there's so many of us working on so many things, that if we put enough effort into it, we will solve problems, if the problem is there to be solved. That's why it's so important to have governments involved. It's not just giving the right person the dollars. It's actually giving a lot of people the ability to work on problems. That's how things get solved. Not because they have to work together, but because there's so many possibilities that we need to trace down. And so that's why I think nations take Nobel Prizes so seriously. Because to win a Nobel Prize isn't about having the smartest people. It's about having sustained lots of effort, lots of well-educated people, so that you are the one who gets to make the breakthrough.
Yes, sir.
Have maybe one or two questions. So, yes, another high school student.
Thank you very much for the speech. I would like to ask on one part that you say that to solve the human problems is to distribute the prosperity throughout every person. I would like to ask by what means do you think that humanity can achieve it? Since, like, for example, geographically, we are different. Culturally, we're also different. And by financial basis and even genetics, we are different. What do you think is the way that we can share the prosperity and help each other in order to solve the problem for the whole community, rather than just solving one's greed?
So I think ultimately this is an ethics or a moral question. It's not a scientific question. It's a question about looking at the situation and realizing the best long-term solution for you, as perhaps a rich person, is to share some of your wealth, some of your future wealth especially, with those less fortunate. Because by making them richer, they will need less in the future. So it's about essentially sharing. So right now, when countries try to decide what their view would be, for example, in trade negotiations, we all know the reason the trade negotiations are happening at all is because economic theory tells you that if we work together cooperatively, everyone is better off. So that's why people get together. But when they're negotiating, each trade minister is trying to get special treatment for their own country. Now, to the level where everyone gets together and those trade agreements actually deliver something collectively everyone can agree on, they really do move the world forward. They make us all able to share what we have better. But often, they don't move. Why? Because one country is wanting too much compared to what other countries are prepared to do. The negotiations that we're talking about to spread the wealth are similar. If we in Australia, for example, one of the richest nations on the planet, decide it is in our best interest to poison all discussions on putting a price on carbon because we have more coal than any other country on the planet, that in the short term will make Australia rich, but in the long term will make us poor, because everyone in the world will have this. And that is a decision of morality we as Australia and every nation here on the planet need to come to terms with. It's hard. I have no solution, but like most things, it requires the people to think about it, and to believe in it, and it requires leadership. Leadership that is prepared to listen to the people and to lead for a long-term vision rather than short-term gain, which is so much easier to do within the political landscape.
Thank you very much.
Okay, we have time for one last question, please. Yes.
So as a high school student, it's really hard to find resources and data to do stuff. And I'm just wondering, where can one find analytical data in terms of astronomy to use for research?
All right, so one of the amazing things about the World Wide Web, and I'll remind you, CERN, 8 billion euros to discover the Higgs boson. Why'd we do that? Well, they did develop the World Wide Web, which is more than $1 trillion of income worldwide each year. Pretty good return on your investment. The World Wide Web means that almost everything scientific is shareable now. Every paper written in Nature, you have to put the data online. Most of the US, much of Australia, much of the EU, all of the data for science goes online. So for astronomy, you can download the data coming from the Rosetta mission. You can look and analyze it yourself. That's all there. In my case, I'm doing a digital map of the southern sky. We will be putting every bit of the petabyte of data online, which you will be able to download. You're going to have to wait a year or two, but while you're waiting, the Sloan Digital Sky Survey in the US has already made their data available. You can get a picture of every part of the northern sky that's been observed from them. The Hubble Space Telescope, every bit it's ever taken is available to you to download. We are in a new era where all this information is shared. The hard part is not the availability of data. The hard part is being able to ask the data an interesting question. That turns out to be much harder for you to do, but I would encourage you to try it nonetheless.
Okay, I was requested that our question could be asked because we like it to be interactive floor, so please, and we have a few in the front. So let's do the back first and the microphone in the front later. ขอไมโครโฟนข้างหน้าหลังจากนี้ No, อันนี้โอเค
All right, first of all, it's a great honor, great to be here. I'm actually quivering with excitement and
Me too.
Yeah. So the question that I'd like to ask you is that I've always wanted to ask a Nobel Prize winner that what really is the way, like how do you like overcome your mistakes? How do you have that surge that makes you go on even though you fail so many times? And another question that I have is that, is peace in the end possible by any chance?
All right, well, failure, if you do not fail, then you're not doing a good job. That's the first thing to realize, is if you're not failing regularly, then you're not taking risks. Now, when I say fail, I mean fail quickly, gracefully, not spectacularly. Okay? Because it turns out when you fail spectacularly, you often don't get a second chance. But on the other hand, it's worthwhile trying little things that you're not sure you're going to succeed at. And what you need to know, and this is something that takes practice, is when this is going good or when it's going bad. But if you see failure as something that indicates you're doing the right thing, then it's not so hard to fail. It's disappointing, but it makes you want to do it again. And so I've always been willing to fail. But in the motto, when I visited Google, Google's model that they tell all their new employees is to fail often, but fail quickly. It seemed to have worked for them.
All right, thank you so much.
So we have a few questions in the front. Yes. Okay. Second row. แถวที่ 2 ค่ะ
What is my advice for a high school student interested in astronomy? If you love astronomy, you should be prepared to do it. People around you will say, but there's no jobs in astronomy. Well, that's actually not true. There aren't a lot of jobs in astronomy, but there are some, and there are some jobs here in Thailand. There are jobs around the world. But you always have to be prepared to fail. The good news is if you get a degree in astronomy, you've learned this incredible skill set that turns out to be very valuable. Last year I went through to make the point of looking at the graduates of my university, Mount Stromlo Observatory, and looking at the employment rate of all of our graduates. Our employment rate was 100%. There are a few people who were dead, but everyone else was working. It turns out that physicists, especially if you get a PhD, which is where you get really skilled up, the rate of unemployment in the United States, where there's very good records of it, is about 1%. And that is the lowest of any discipline. So if you love it, then do it. It's a useful career, but you have to be prepared not to do astronomy. You have to be prepared to use your skills to do whatever life throws at you. And that was my intent. I never intended to become an astronomer. Life has allowed me to do it. But think of the alternative. Imagine astronomy is what you want to do more than anything else. And people say, it's not practical. So you do something that you don't like as well. Are you going to do it as well? The answer I would say is almost certainly not. What happens if you do astronomy and you do it well? Then you will train yourself up as best as you can. And the worst thing that can happen to you is you're going to have to get a job like what you were going to do if you just didn't go study it in the first place. So the worst possible thing that can happen to you is you got to get a job that isn't absolutely the perfect thing you saw in life. And the only thing else you could have done was just to go straight to that job. Seems to me like a, there's no reason not to try. Okay? And that's one of the beautiful things of especially a high-end science degree, is they give you large numbers of options. I can't guarantee you they will give every single person in the audience a great job, and you have to love it. You have to be good at it. But if you are, it's really about as good an option as there is. Right? So don't be scared.
We have more questions from the second row. Yeah, back there. Oh, we'll get to you soon. So.
Okay. Thank you. I have an astrophysics question. Your research confirmed about the existence of dark energy, but we still don't know what dark energy is. So what are the tools that we need to go further and to answer the question about dark energy?
So, one of the reasons I was rather surprised that I won a Nobel Prize is the thing I discovered, dark energy, I can't tell you what it is. It's energy that's part of space itself. Why it's there, how it acts in the long term is a mystery. So it seemed to me kind of a silly thing to give the Nobel Prize for when we really didn't know what it was. But fortunately for me, the Nobel Prize Committee disagreed. So what is this stuff? So we can have ideas and we can test them. So one of the ideas is that there is some particle out there, like the Higgs boson, but not the Higgs boson, that leaves behind energy in its wake, in the same way it turns out the Higgs boson does. And if that particle exists, it turns out we're not going to be able to create CERN, but we could potentially infer its existence because the energy will change as the universe expands. And so imagine we can measure very accurately, back in time, how the universe is expanding and how it's accelerating. We can, it turns out, infer if the energy of space is changing back in time. If the energy of space were to change by 10%, we can measure that. The problem is the theories behind this say it might change by 30%, or it may change by 1 part in a billion. Now, 1 part in a billion we're never going to measure. So we are out measuring very accurately how much of this dark energy space has back in time to see if we see it changing. The basic model we have is from Albert Einstein. His basic model, which we don't really understand why it's there, but it predicts it stays the same. At this point, every measurement we've made says it stays the same. If we continue to see that, then the hope is for some brilliant mind somewhere on the planet to have an idea of why it should be there. That is an Einstein-like insight. That is my best guess of how we solve it. Someone's going to have an idea. And then we'll be able to test it. But until that happens, I don't know. Reality is a little confused for me right now because I can't quite test what's going on like I would like with dark energy.
Okay, here we have a microphone for you.
I'm from a country. Science, science. I studied physics from the State University. Two of my colleagues are professors in mathematics, physics, chairman in the mathematics department. The other one is astrophysics at Harvard. How do I know? Barbara Collins, who's secretary to physics department, will say he will come in and tell me which is Harvard. Now, to me, science is a way of solving problems. We may not solve every problem. In your culture, we can't take it lying down. We have to try and solve it. Now, back to Thailand. I study from physics. There are good people who ask me, what do you study physics? What is physics? Yes. And there are some good people who tell me that physics is useless in Thailand. Why we should study physics? And I'm shocked. I'm shocked. My question is, what is, perhaps I should tell you that I'm former director of the Institute for the Promotion of Physics, Science, Technology, and good time trying to promote science in Thailand. I ask you, sir, how would you go about developing science in Thailand, a country that have a strong tradition in science?
So, it's a hard question, and of course, you know the Thai culture far better than I do. But I will say that I have taught Thai students in astronomy, and although as a nation supporting scientific endeavor, it has perhaps not put as many resources into it as, for example, Australia or the United States has. But the fundamentals of interest in science is here. It's in every 10-year-old, it's in this audience, it's in the Deputy Prime Minister, so it's there. But it is very difficult to justify the patience required to do science when countries are developing. Now, Thailand has moved from being a developing nation of the past to being what most people would consider a developed nation. Maybe not as developed as the richest countries in the world, but still developed. So I see this country having the patience to invest in science. And when you have the patience to invest in science, then you have the ability to reap the rewards. But it takes patience. How do you do this? Well, you have events like this. You have ministers like we have here. We have a thought, a belief within the country that it is an important thing to do. It needs to be at all levels. We have to support good education. We have to support strong universities. We have to make it essentially a matter of national importance. And that's what you need to do. It doesn't happen overnight because the benefits do not accrue overnight. If Thailand suddenly decides to invest 3% of its GDP in science today, it will make the country rich 30 years from now. But it will not make it rich tomorrow.
Okay, the time is now 3:30, so I have to end the discussion floor. So we thank you, Professor Paul Schmidt, for the full lecture today. And now I'd like to invite the chairman of the Kasetsart University Council, Professor Dr. Niwat Rungpadip, to give the token of appreciation to our guest today. First souvenir is the painted porcelain called Benjarong, Thai painted one, for your memory of Thailand. And a token of appreciation from Kasetsart University. Well, before we end today, I'd like to invite our distinguished guests on stage. Could you please remain on stage, please? It's now time that we would like to take a photo of all distinguished delegates in the front row. Would you mind taking the stage for the group photo? Thank you, Professor Brian Paul Schmidt, and thank you all distinguished guests for joining us today. Now it's time that we would conclude our special lecture today. On behalf of Kasetsart University, I'd like to thank all participants for joining us today, and there will be refreshments served in the hallway. Thank you very much. I wish you a wonderful afternoon. สวัสดีค่ะ